Okay, in our final example for the separable differential equations lesson, we've got a free response question from a couple years ago. It says BC4, but it was also on the AB test in the exact same position. Since it was the fourth question, definitely calculator inactive. Let's take a look at it, shall we? At time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. Okay, so I gave you a nice little scientific illustration of the different parts of the potato just in case it might help you on this question. The internal temperature of the potato is 91 degrees Celsius at t equals 0, and the internal temperature of the potato is greater than 27 degrees Celsius for all times t equals t greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies the differential equation dh dt is equal to negative 1/4 h minus 27, where h of t is measured in degrees Celsius and h of 0 is equal to 91. All right, all that's just the setup to the equation, to the problem. Let's take a look at what the question's actually asking us to do. Part A, write an equation for the line tangent to the graph h at t equals 0. Should be easy. Tangent lines is just point-slope form, right? Write this equation to approximate the internal temperature of the potato at time t equals 3. Okay. Part B. Use the second derivative of h to determine whether your answer in part A is an underestimate or an overestimate of the internal temperature of the potato at time t equals 3. All right. A little redundant, but that's okay. Let's see. Part C. For t less than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies the differential equation dg dt is equal to negative g minus 27 to the 2/3 power, where g of t is measured in degrees Celsius and g of 0 is equal to 91, just like it was before at the very beginning. Find an expression for g of t. Based on this model, what is the, altogether now, internal temperature of the potato at time t equals 3? All right, let's go ahead and tackle this problem, shall we? So we'll pull up our note page here. And in order to get started here, I need to first label this as example 8. And then let's write down a couple of key things. So first of all, we want to write down our differential equation, which was dh dt, if I'm not mistaken, is negative 1/4 times h minus 27, is that right? Yeah, h minus 27. Now, I'm going to write down a few extra pieces of information here, like we have our initial condition. And our initial condition was h of 0 is 91 degrees Celsius, I think. Boop. Okay. All right. And then there is actually another piece of essential information, something that was probably very easily overlooked, which is right here. It is the internal temperature of the potato is greater than 27 degrees Celsius. It's probably going to come up. We'll see here. So I'm going to write it down for sure. So h of t is greater than 27 degrees Celsius. That must be the room temperature there, so it's never going to fall below that. For t is greater than 0. So here's our important information box. I'm going to box it there. All right, stuff is going to come up for that. Okay, so let's go ahead and tackle part A. We're going to write the equation of a tangent line. So to write the equation of a tangent line, we just need two pieces of information. We need a slope and we need a point. All right, we already have our point. It's given to us right here. We just need the slope at that particular point, which is what the differential equation is for. So the slope, of course, is going to come from dh dt such that t is equal to 0 here, make that look like a 0, is equal to, now let's just plug 0 into our differential equation. Negative 1/4 times, wait, there's no t. There's an h. If only I knew what h was equal to when t is equal to 0. Actually, I do. It's right there. It's our initial condition. H is going to be equal to 91 when t is equal to 0. So I'm going to plug a 91 in here, minus 27. And let's do some arithmetic. Sure, you can safe stop that, but my gosh, this is going to make this look nasty. So I've got 91 minus 27 borrow. I'd get a 4. So it is a 64. Negative 1/4 times 60. What? 60 parentheses? 60. Come on. 4. Which goes in there 16 times the negative 16. There's our slope. So let's just write our equation now as y is equal to, maybe I even label this, so tangent line y minus y1, which is 91, is equal to our slope, negative 16, times x minus x0, which is 0. Sure, I can leave it like that, but maybe I just go ahead and isolate the y. I'm probably going to go ahead and do that because it's asking us to approximate what this is equal to at t equals 3. So I would have negative 16t. I put x's. These shouldn't have been x's. This should have been t's. So I'll make that a t. Plus 91. And I'm also going to make that look like a prettier one. And then I'm going to box it because they asked for it. It's essential. And use this equation to approximate the internal temperature of the potato at t equals 3. So I'm going to say that h of 3 is approximately equal to negative 16 times 3 plus 91, negative 48 plus 91, and I got 91 minus 48. Borrow 1 again, a 3 and a 4 to get a positive 43 degrees Celsius. So our conclusion here is that h of 3 with this basically local linearity idea is approximately equal to 43 degrees Celsius. Okay, point breakdown for this, whoa, what the heck? Point breakdown for this one went like this. I think this one was worth a total of 3 points. Getting our slope was worth a point. Getting our equation of our tangent line was worth a point. And then finally, our approximation was worth the final point. Okay, which brings us to part B. On part B, it says to use the second derivative to determine whether that answer that we just got was an over or under approximation. All of that means, oh wait, an over approximation or an under approximation of what, did you ask? Well, the internal temperature of the potato, of course. So I need to start by just actually finding our second derivative. So I'm going to write this down just one more time. dt is equal to negative 1/4 of h minus 27. And then if you would prefer, negative 1/4 h plus 27 over 4, if I were to distribute there. And I want to call your attention to a couple things. This h that's on top is the dependent variable, which means that it gets differentiated implicitly. And I point that out simply because there's no t's in there, so the t down at the bottom indicates the independent variable, which would be differentiated normally. And there's no t's in this equation. All of that goes to tell you that the second derivative of h with respect to t goes like this. So it's just right over here. I have negative 1/4 times h. Its derivative should just be negative 1/4. But then I have to use the chain rule because I'm differentiating this implicitly, times dh dt And then, of course, the derivative of 27 over 4 is just 0. And then, you know, like we usually like to do, I'm going to take this dh dt out and replace it with what it is equal to, which is the negative 1/4 h minus 27. Negative 1/4 times negative 1/4 h minus 27. Close those parentheses. Excuse me. And then giving our final handsome answer, it goes like this. dt squared is equal to a positive 1/16 h minus 27. Okay, so there is our second derivative looking real nice. And then we're supposed to be able to use this to determine whether we made an over and under approximation. Well, we used a tangent line. When you use a tangent line, let's say that we have ourselves a graph that looks sort of like this. And let's put a graph in here. And then I'm approximating the value of our function with a tangent line. So let's say our point of tangency is right here. And so we're trying to see, whenever I step away from that particular point, did we over or under approximate this value of this function? And it's based on concavity. It's whether or not the graph bends upwards away from your tangent line or downwards away from your tangent line. And concavity, we're going to get that information from the second derivative. That's the whole reason why they told us to find the second derivative. And I just need to be able to see, is this thing always going to be positive or is it going to be negative? You might be asking, like, how am I supposed to know that? It's got h minus 27 in here. Depends on what the value of h is, right? If h was ever less than 27, this is going to be negative. But wait a minute. Let's scroll back up here to our important piece of information. And what I said, or what it said, is that h, no matter what, is got to be greater than 27. Okay, so now if I come back down here, since h has got to be greater than 27, this quantity is always positive. So since it's always positive, our second derivative is always greater than 0, which means that this is concave up. It just happens to be very similar to the picture that I just drew here. And when we have our tangent line, it's down below, and our tangent line is going to under approximate the value of the actual function at that point. So I just want to kind of wrap this up, summarize it. I'm going to say that since our second derivative is greater than 0, h is, maybe h of t, huh? H of t is concave up for all values of t greater than 0. Thus, I don't think thus has an e on it. Thus, h of 3, which was approximately, what the heck was it? Like 43 degrees, I think, is an under estimate. Does it say estimate? Yeah. Estimate. Of the actual value of h of 3. Nice. Okay, so it was based on concavity, and I pointed out that it was an underestimate. So what was the point breakdown for this one? Guess what? All of this information, 100% of all this, it was a lot of work, was worth 1 point. It was the answer with the justification. That was it, 1 point for all of that. My gosh. All right, let's go ahead and take a look at the last part of this again. So here they gave us a second differential equation, an alternate model, and it's actually asking us to solve this differential equation. So let's just take a look at the points that we have so far. There were 3 for the first part, 1 for the second part. That's 4 of them, which means that this last part was worth 5 points. Okay, so part C, our differential equation, dg dt is equal to negative, parentheses, g minus 27 to the 2/3 power. And it is asking us to find an expression for g of t. So we are solving this thing for g of t. What is the function that gives rise to this differential equation? So what is your first step? Your first step, of course, in solving a differential equation, is the point of this whole entire question in the context of this lesson, is to separate your variables. Separate variables. As a matter of fact, if you do not separate your variables at this point, you get exactly 0 points for part C. So the only separation that needs to happen, actually no, there's 2 separations that need to happen. Our dt needs to come over there to the right-hand side, and then everything else left over is g stuff. So the dg stays, but this other this g minus 27 to the 2/3 power needs to move itself over there to the left side of the equation. So I'm going to have dg, and I get it over there by dividing, over g minus 27 to the 2/3 power. And notice that I'm going to leave the negative over here on the right-hand side, all right, because it's going to be really easy to deal with that negative when it's just attached to a dt. All right, I have separated the variables successfully. I gained my first point. Now I'm going to take the antiderivative of both of these sides. And on the left, I think that it might be easier if I rewrite this in terms of like putting that up at the top. So g minus 27 to the negative 2/3 dg is equal to, and then I'll go ahead and differentiate the other side. It's going to be easy enough as it is. So negative t, and then don't forget your plus c. And speaking of points here, if at this point you forget your plus c, you get no more points for the whole rest of the question, okay? They're trying to make you understand that plus c is super important. Now, on the left-hand side, when I go to take the antiderivative, it looks like I need to do a u substitution because it's a composite function. Our u is equal to g minus 27, and our du is equal to just dg, which means that we really didn't need to fix anything. This is just u to the negative 2/3 power. So whenever I take its antiderivative, using the power rule, add 1 to that exponent, it's to the 1/3 power, g minus 27 to the 1/3 power divided by 1/3, which is the same thing as times 3, is equal to negative t plus c. All right, so now I've successfully found all of my antiderivatives. Let's go ahead and stick in our initial condition, right? The earlier, the better. So our initial condition was 0.91, just like it was in the previous question, right? In the previous part, so right there. Let's plug it in and simplify here. So blue. I would have 3 times, now this is, the 91 is our g, so 91 minus 27 to the 1/3 power is equal to 0 plus c. So there's our c, and probably want to go ahead and simplify this. And didn't we say this was 64 before? So 91 minus 27 is 64. So I think we've already done that subtraction. And then 64 to the 1/3 power. So in other words, what number raised to the 3rd power is equal to 64? I think that's 4. We got 3 times 4. 12 is equal to c. So there's our constant of integration. No. Choose your colors. There we go. And then we want to rewrite our equation. So rewriting 3 g minus 27 to the 1/3 power is equal to negative c plus 12. Okay, all right, and you might think that you're done. As a matter of fact, you're going to get most of the points at this particular moment if you stopped right there. However, it does say, I'm going to come back up here, find an expression for g of t, and I did highlight that. That means that, like what we did in some of the previous parts of this lesson, that you have to solve it for g of t. You have to isolate it. You have to get it explicitly. So I'm going to divide both sides by 3. G minus 27 to the 1/3 power is equal to negative t over 3 plus 4. And then I'm the type of guy that's probably going to reverse those so that my leading term is going to be positive. It's okay, whatever. If you don't, you're fine. And now we've got to get rid of that 1/3 power by cubing both sides of this equation. G minus 27 is equal to, I'm going to have 4 minus t over 3 cubed, right? And then the final step is to add the 27 over. So I have g, I'll write it as g of t, is equal to 4 minus t over 3 to the 3rd power, all of that plus 27. There we go. We have successfully isolated g of t. And then I think we're done, right? We're done, except we're not. Based on this model, what is the internal temperature of the potato at t equals 3? So we, one more time, have to use our equation to approximate the internal temperature of the potato. This is not an approximation at this point because we could just get it. 4 minus 3 over 3, all of this cubed, plus 27. And let's see, that would be 1. 3 over 3 is 1. 4 minus 1 is a 3. 3 cubed is 27, plus another 27. 40, 54, 54. So we're going to say g of 3 is equal to 54 degrees Celsius. So remember that in a previous part of the question, I think it was part B, it was asking us, did we under or over approximate? And we had 43 degrees, and we said it was an underestimate, which meant that the actual temperature of the potato was, internal temperature of the potato, I should say, was supposed to be bigger, and we did get a bigger value, so it's reasonable. Let's see what the point breakdown was for this part. So, like I said, the act of separating the variables was worth 1 point. That was the first point. And if you didn't separate the variables, you got no points for the rest of the question. The second point was finding the antiderivatives, so plus 1 for the antiderivatives. So that's at this point. Actually, let's move it down right here because this is where the antiderivatives came in. Plus 1 for antiderivatives. And then you got your third point for using your putting a constant of integration and using your initial value. So plus 1 for c and initial value. Depending on how many points they have available, sometimes those things are separate. This one was combined up in just one single point there. The next one is having an equation involving, having some sort of final equation involving g and t. In other words, you could have that written not explicitly, just having g and t in the equation, like we had right there. That was worth a point. Then actually solving it for g was worth another point, so an expression for g of t. And then your final point was your approximation, not your approximation, your evaluation to get g of 3. Is that correct? I think that might be too many points. Let's see. 1, 2, 3, 4, 5, 6. Yeah, that is incorrect. So this final point for g of t, that was g of t and g of 3. Both of those were combined up to make one. The last point for that one. Which brings us to the end of our lesson on separable equations. So we learned that when we solve differential equations, at least the ones that they're going to give us on the AP exam, step number one is to separate those variables. Get all the y stuff on one side, get all of the x stuff on the other side before we take the antiderivatives of both sides. Now remember that as part of your homework assignment, please take a look online at your homework supplement to get a little AP FRQ practice with these concepts.